to Chapter 5, Gas Laws. We are going to talk about the gases after talking about reactions in aqueous solutions. We need to talk about the gases and the gas laws. A little bit of introduction. What I need to tell you is the gas pressure. What we call gas pressure is the collision of gas molecules to the container wall. You know that gas molecules freely move, so these free motions let them to collide to the container wall, whatever the container is. Even the room you're sitting at, the gas molecules, the air molecules collide with the walls of the ceiling and the floor of the room. So, since gas pressure is important for us, let's review the physical formulas we had, the physics formulas, let's say. Pressure, which is force over area, and also pressure can be the product of density by gravity by height. So these are the two formulas to calculate the pressure. What we need here is how to deal with the SI units for pressure. We have the most common unit for pressure, which is atmosphere. We show it with ATM. mmHg or millimeters of mercury, torr, and bar. The most common units that we work with is atmosphere and millimeters of mercury, and millimeters of mercury and torr are the same. One more thing is that 1 atmosphere is 760 millimeters of mercury. In the exams, these are normally given, these conversions between the units. So these two are the most important SI units for pressure. Another pressure is Pascal that we show in PA, but again, we work with these two more often. So let's start working on the empirical gas laws. Why do we need to study the gas laws? Because gases' behavior depends on the changes in the pressure, temperature, volume, and number of moles. So gases behave differently in different pressure, temperature, volume, and number of moles. For each law, we will keep two of these variables constant, and we will study the behavior of gas based on the other two variables. Like what? Like the first law, Boyle's law. Boyle's law was derived under constant temperature and moles of the gas. According to Boyle's law, pressure and volume of the gas have an inverse relationship. So the product of P times V is always constant, and you can say that initial pressure times volume is going to be final pressure times volume. So PIVI is equal to PFVF. Keep in mind that in gas laws, this is the only law that shows an inverse relationship. Because I'm going to introduce the rest of them, and you'll see the rest of them show a direct relationship. But Boyle's law is the only one that shows an inverse relationship. So let's see how the diagram shows if P is proportional to the inverse of volume. What you see here is, like, let's say this point. It shows in high volumes, pressure is low. I always bring this example of a cylinder because that's an easy example to understand. So a cylinder, if you have a big volume, the pressure is low. But if you move along this graph, you have high pressures and low volume. So this is for compression of a cylinder. In low pressures, you have big volume, and in high pressures, you have low volume. So you see, these two, pressure and volume, work the opposite of each other. That's a graph that I wanted to keep in mind. It's not a straight line, it's a parabola. So let's work on an example on how to apply this PIVI equals PFVF. A volume of oxygen gas occupies 22.4 milliliters. So I will put it as VI at 524 millimeters of mercury. So this is your PI and 21 degrees Celsius. What is the pressure if the volume changes to, this is VF, while the temperature remains constant? What is the pressure means find PF if the temperature remains constant. So it means that you're looking for the relation between pressure and volume, so you need to apply Boyle's formula. PIVI is equal to PFEF. You're solving for PF by plugging in and calculating. You will end up having 1,048 millimeters of mercury as the pressure. All right? Because the volume is half of the initial volume. You can work on it at your own pace and then move towards the next law, which is Charles' law. I told you in each law there are two of these variables kept constant. For Charles' law, pressure and moles were kept constant, so they came up with these, that volume and temperature have direct relationship or proportionally, directly proportional to each other. So VI over TI is equal to VF over TF. Something that I have to mention at this point is that temperature is called absolute temperature, so its unit is in Kelvin. You cannot use degrees Celsius in gas laws. Whenever you see capital T in the gas laws, you need to change your temperature in degrees Celsius to temperature in Kelvin. And you know that T in degrees Celsius plus 273.15 will be temperature in Kelvin. You learned it in chapter 1. So, here's the graph. For Boyle's law, you saw a parabola. For, let's say, for these four experiments, working with 1 gram of oxygen, for 1 gram of carbon dioxide, 0.5 grams of oxygen, and half a gram of carbon dioxide. These are the graphs up to these points, and the rest is extrapolated to x-axis, to temperature line. It shows that if you keep cooling the gas, they will all reach to one point, which is minus 273.15 degrees Celsius. This is a very, very, very cold temperature and shows the volume at this temperature is going to be 0, hypothetically. Nobody has reached this temperature yet, and nobody has seen a 0 volume for a gas. But this is called absolute zero. Have you ever heard of absolute zero? I'm sure you have. Absolute zero is minus 273.15 degrees Celsius, which is the coldest temperature, but nobody has reached it yet. Because hypothetically, volume of the gas at this temperature will be 0, which is a little bit like impossible, right? Let's work on an example on Charles' law. Carbon dioxide is prepared by adding hydrochloric acid to calcium carbonate. At 0 degrees Celsius and 760 millimeters of mercury, 65.8 milliliters of carbon dioxide is obtained. So TI is 0 degrees Celsius and VI is 65.8 milliliters. Sorry. What would be the temperature? So what is TF if you obtain 82.4 milliliters of this gas? Don't forget you're dealing with temperature, so the first thing is that changing the initial temperature to Kelvin. 0 degrees Celsius plus 273.15 gives you 273.15 Kelvin. Then you plug it into this formula. When you have you're solving for TF, you need to do the cross multiplication. The known side, TIVF, divided by what comes on the unknown side, divided by VI. plug, calculate, and you will end up having 342 Kelvin, that's it. 342 Kelvin, even. Calculate it one more time at your own pace and make sure your calculations are correct. The next law, which comes on your PowerPoint slides without a formula, is called Avogadro's law. Again, two of the factors are constant, pressure and temperature. And under constant pressure and temperature, equal volume of the gases have the same number of moles. So we assume we have a cylinder which is sealed, the pressure and temperature kept constant, so we will have the same number of moles of gases, two different gases in a cylinder, then you will have the same number of moles. This is Avogadro's law. The questions are very similar to what you have solved before. Now, if you combine Boyle's law, Charles's law, and Avogadro's law, if you have Ni over Ti, we normally don't show it here, but Nf Tf, okay? So PiVi over Ti is equal to PFVF over Tf. Now, my suggestion is that don't need to memorize Avogadro's law, don't need to memorize Charles's law or Boyle's law. You just need to memorize combined gas law. And then you will be safe any type of question given to you. For example, if you have a question and it says temperature is kept constant, what do you have? Boyle's law, right? PiVi is equal to PFVF. If you see pressure is kept constant, what would you have? Vi over Ti is equal to Vf over Tf. So you will have Charles's law. And I told you, you can keep Ni and Nf, but normally when we don't talk about number of moles, they are kept constant as well, which is the case most of the times. Ready to work on a question? If a gas in a cylinder at 15 degrees Celsius and 6.5 atmosphere has a volume of 12.8 milliliters, what would be the volume if the cylinder expands at 22 degrees Celsius and 8.6 atmosphere? So let's see what we have, what we are solving for. This is the initial temperature. Like to color code it. Initial temperature. 6.5 atmosphere is initial pressure. And initial volume is 12.8 milliliter. It says initial. Okay. What would be the volume? So we are solving for Vf. If the cylinder expands at, this is T2, Tf, let's say, and this is Pf. And we are solving for Vf. So PiVi over Ti is equal to PFVF divided by Tf. The first thing you do is to change these temperatures to Kelvin and then plug it in. Again, you are doing a cross multiplication, PiVi times Tf divided by Ti Pf. Known side divided by what comes on the unknown side. Then you plug in chalk and calculate. You will end up having 142.03 milliliters, which is almost like 0.14 liters. But if you're not asking for a specific unit, you don't have to change anything except the temperature, because the two sides have the same units, will be canceled. You see here, the Kelvin and Kelvin are canceled, atmosphere and atmosphere will be canceled. So you don't need to do extra conversions or changing the units. All right, we reached to our last law, which is called Ideal Gas Law. Ideal Gas Law is talking about just one condition. For all of the laws before, for Boyle's law, for Charles's law, and for combined gas law, you had two different conditions, right? Initial and final. But for ideal gas law, you're just dealing with pressure, volume, number of moles, a universal gas constant, and temperature. So R is gas constant. There are different values for gas constant based on the units you use. If you use liter, atmosphere, mole, and Kelvin. If you use liter for volume, atmosphere for pressure, mole for mole, and Kelvin for temperature, the value of R will be 0.0821 liter atmosphere per mole Kelvin. But if you use joules and mole and Kelvin, then the value for R is going to be 8.3145 joule per mole Kelvin. These constants will be normally given in the exams because the students have some problem memorizing them. But be careful. If you're using, for example, this value for R, make sure the rest of the units will be aligned. With these units. You see? You should be the same. You cannot use the temperature in degrees Celsius, or you cannot use volume in milliliter or pressure in millimeters of mercury. They have to be the same units that you see in our unit. I hope it was clear. So let's move on and work on a question. A cylinder of argon at 20.8 atmosphere and 25 degrees Celsius has a volume of 40 liters. What is the mass of argon in this cylinder? So there are two signs that shows you need to use this ideal gas law. First, you don't have initial and final conditions. Second of all, you're looking for the mass. How to find the mass? The best way to find a mass is always from moles. And in which gas law you see the number of moles and pressure and volume? It's the ideal gas law. So you're solving for n first, and n is going to be PV over RT, the known side divided by unknown side. Don't forget temperature must be changed into Kelvin. So you plug it in, and number of moles will be 34 moles. But this is only the number of moles. Don't forget that you are supposed to find the mass. Then moles times molar mass will give you the mass, which is 1358.2 grams. Okay? So this is one of the uses of ideal gas law. How did I find 39.94 for molar mass? From periodic table for argon in group 18. One more thing. If you see these three letters, STP, these three letters contain two important pieces of information for you. Standard temperature and pressure. Standard temperature is 0 degrees Celsius, which is 273.15 Kelvin. And standard pressure is 1 atmosphere. So, under STP conditions, under standard temperature and pressure conditions, 1 mole of each gas, regardless of the nature of the gas, whether it's argon, carbon dioxide, hydrogen, methane, propane, any type of gas you think of, 1 mole of that gas under STP conditions will occupy 22.4 liters per mole, which is called molar volume. We show it in VM, molar volume. So don't forget, it's only for STP conditions. If the temperature or pressure change, you won't have 22.4 liters. So if you're solving the questions for STP conditions, you don't need to ask what is the temperature, what is the pressure. They're already given in these three letters for you. And one thing that I expect you to memorize is that under STP conditions, 1 mole of each gas, regardless of its type, will occupy 22.4 liters, which is called molar volume, volume of 1 mole. Okay? So, let's move to the last part of this portion of the video, which is gas density. Gas density is calculated from this formula. Please keep it in mind. It's pressure times molar mass divided by R, which is 0.0821 liter atmosphere per mole Kelvin, times the temperature. So D is PM over RT. MM is molar mass of the gas. At the end, I would like to work on an example with you based on this formula. Let's see what we have. What is the density of propane gas at 120 degrees Celsius and 4.2 atmosphere? What is the pressure? 4.2. What is a molar mass? Molar mass of 3 carbons and 8 hydrogens. If you add them up, it will come up to 44.11 grams per mole. R is 0.0821 liter atmosphere per mole Kelvin, and temperature is 120 plus 273.15. You remember temperature must be always converted to Kelvin. So density will be 5.74 grams per liter. I hope you had a better understanding of the gas laws. Again, you don't need to memorize all of the gas law formulas. Combined gas law is going to squeeze Boyle's law, Charles's law, and Avogadro's law for you. And then you will have ideal gas law, which you can memorize, and the conversions will be given to you. Don't forget to practice enough until you master these gas laws.